Hello, ladies. Today we're going to be talking about 6 function operations. Yes, I am recording this at the hospital. And yes, my baby girl has been born. If you'd like to see her, here she is. All right, but today we've got to talk about something very, very important, function operations. So let's talk about function operations real quick. You can always add, subtract, multiply, and divide functions based on how you perform these operations for real numbers. One difference, however, is that you must consider the domain of each function. For instance, if I was adding things, I would just add the functions together. If I was subtracting functions, I would literally just subtract the functions. Multiplication, I would multiply them together, and division, I would divide the function. Now, the part that I mentioned, you have to consider the domain of each function. If I throw g of x into the denominator here, g of x cannot equal 0, right? So if g of x were to equal 0, then of course this guy, f of x over g of x, would be undefined because you would be dividing by 0, which is why you've got to take the domain into account. So the domains of the sum, difference, product, and quotient functions consist of the x values that are in the domains of both f and g. Also, the domain of the quotient function does not contain any x values for which g of x equal to 0. All right, so let's add and subtract these functions on this first example. So let f of x is equal to 4x plus 7, g of x equal to square root of x plus x. We're asked what is f plus g and f minus g, and what are their domains? Well, first off, let's figure out the domains of each function. For f of x, we've got 4x plus 7. Is there any x value that I can plug into x which would give us an undefined answer, or an imaginary answer, or some other type of answer where math fails? The answer to that is no. So f of x has an unlimited domain, right? So its domain literally goes from negative infinity to positive infinity. G of x, however, if I was to plug in a certain type of number into x, I would end up getting an imaginary solution. You know what I'm talking about here. If I were to plug in a negative number into x, I would end up with a square root of a negative number, and that can't happen. That would give me an imaginary number. So that changes the domain possibilities here. I can only have a domain here from 0 to positive infinity. All right. So if I go to add f of g of and f, or add f and g and subtract f and g, I would get f plus g is equal to 4x plus 7 plus the square root of x plus x. Notice all I'm doing here is adding f of x to g of x. All right. Simplifying is very simple. We combine like terms. So 4x plus x gives you 5x plus 7 plus the square root of x. That's it. The domain here has to take into account both of the domains that we have. Go with the stricter of the domains. So in this case, we've got a domain going from 0 to positive infinity. That covers all the domain possibilities that we can have. A better way to write this, however, instead of using interval notation, you would write this in inequality notation because it really explains exactly what x can and cannot be. All right. So how we would write this is that x has to be greater than or equal to 0. Subtracting f and g, we do the same thing. 4x plus 7 minus. Now be very careful here because when we're subtracting an entire expression, we've got to distribute that negative through. So what I usually do is I put the minus sign, and then I open parentheses and put the expression itself. So it's square root of x plus x, close that parenthesis, and then simplify from there. First step being to distribute that negative. So that gives us 4x plus 7 minus square root of x minus x. Simplifying, we get 3x plus 7 minus the square root of x, where x, again, has the same domain. So x has to be greater than or equal to 0. All right, so your turn. We've got this problem. Find f plus g and f minus g and determine what their domains are. I'm going to write the answer on the board. Feel free to pause if you'd like to work this. So f plus g is equal to 2x squared plus 5, or plus x plus 5, where there is no limited domain, right? So we can just say that x is all real numbers. Okay? All right, and f minus g of x. Actually, a better way to write this would be x is an element of all real numbers. All right, that would actually be the better way to say it. This little curved e means is an element of, so x is an element of all real numbers is how we would write this whenever there's no limited domain. F minus g, we end up with kind of the same idea here. We end up with 2x squared minus x plus 11, where x is an element of all real numbers. There's no limit to the domain. All right, let's talk about multiplying and dividing functions. So, if f of x is x squared minus 9 and g of x is x plus 3, what are f times g and f over g and their domains? So f times g of x, and I'm realizing just now that there is a slightly better way of writing what I'm writing. So I'm going to go back and make a couple of adjustments here. Here, f plus g of x is how we would write this, and f minus g of x. All right. So here we've got f times g of x. This is literally just f of x times g of x, taking into account any domain restrictions that we've got. First off, if we have x squared minus 9, x squared minus 9 is a quadratic. We've talked about quadratics before. Quadratics have an unlimited domain, so we don't need to actually limit that domain. This would mean that x is an element of all real numbers. G of x is a linear equation, x plus 3. We also know that linear equations don't have a limited domain, so we can say x is an element of all real numbers. So when I'm multiplying these, it's literally x squared minus 9 multiplied by x plus 3. Here's the good news. You should know exactly how to approach this. This is just the FOIL method. So we end up with x cubed plus 3x squared minus 9x minus 27, where x is an element of all real numbers, taking both of those domains into account. If I'm finding f over g of x, we could rewrite this as x squared minus 9 over x plus 3. Here, something magical happens. We no longer have an unlimited domain. Cool. We actually can see right from the beginning that if x happened to equal negative 3, this would break our domain because we would have a 0 in the denominator of this equation. So I'm going to say that x cannot equal negative 3. And then from there, I'm going to continue to simplify this. The numerator, x squared minus 9, happens to be a difference of two squares. So we end up with x plus 3 multiplied by x minus 3 all over x plus 3. Now, one thing you should notice right off the bat is as soon as we factor the numerator, we end up with the ability to divide out one of our factors. We've got x plus 3 on the top and x plus 3 on the bottom. Those divide out and we end up with x minus 3. Now, x minus 3, as we know, has an unlimited domain. However, we have already limited our domain in the very first step. So even though we divided out a portion, this still holds true. The x cannot equal negative 3. So we would say x, the f over g of x is equal to x minus 3, where x does not equal negative 3. We actually have to state that. Even though we divided it out, we still have to state that x can't equal negative 3. It's actually really, really important to understanding this. All right, your turn. I'll write the answers on the board if you want to pause and work this problem. So f times g of x ends up being 9x cubed minus 30x squared minus 23x minus 4, where the domain is all real numbers. So we can say that x is an element of all real numbers. F over g of x is equal to x minus 4, but x cannot equal negative 1/3. All right, now for my favorite part of this lesson, let's talk about composite functions. So composite functions are interesting mathematical anomalies that occur whenever you shove an entire expression into another equation. So let's say that we have f of x and g of x. We take f of x and we shove it inside of g of x into the x values there. And you'll kind of understand what I'm talking about as we go through this. But if we look at the diagram here, the diagram shows what happens when you apply one function g of x after another function f of x. So the output from the first function becomes the input of the second function. When you combine two functions, as in the diagram, you form a composite function. So let's say we have f of x. We take the input of f of x and we find the output. Okay, we take the x, plug it into f of x, and we get an output f of x. We then take that output, and that output becomes the input of g of x. All right, becomes the input of g of x. So we're taking the f of x and we're actually plugging it into the x of g of x, which then gives us an output of g. All right, we call this g of f of x. G of f of x, not g times f of x, g of f of x. There's two different ways you can write this notation-wise. One is g of f of x, where f of x gets plugged into the g of x as the x value. Another way we could write this is g of f, and I wrote this kind of sloppy, g of f of x. All right, the open circle here is not multiplication, that's actually the composite symbol. So the composition of g and f of x is basically how we read that. All right, so how to do composite functions. The composition of a function g with function f is written as g of f, like I wrote on the previous slide, g of f, and is defined as g of f of x is equal to g of f of x. These are the two things that I explained on the previous slide. All right. The domain of g of f consists of the x values in the domain of the f, for which f of x is in the domain of g. I know that sounds like a whole lot of mathematics. That's really confusing. You kind of have to actually see this in action in order to understand it. So basically what's happening is you figure out f of x. Once you have f of x, then you plug that into g of x and you get your answer. All right. So let's compose some functions. If I know that f of x is x minus 5 and g of x equal to x squared, I want to figure out what g of f of negative 3 is. Well, according to what we just learned up here, if I'm got a g of f of x like this, I first find f of x, then I find g of x. So that's the order. Whatever's closest to the x is the thing I find first. All right. The x in this case happens to be negative 3. So I'm going to plug negative 3 into f, because f happens to be closer to negative 3. So negative 3 goes into f of x. So I got f of negative 3 is equal to negative 3 minus 5. Negative 3 minus 5 happens to be negative 8. Then that answer, negative 8, becomes the input for g of x. So that becomes g of negative 8 is equal to negative 8 squared. And negative 8 squared happens to be positive 64. That's how this works. So you find f of x, you then use that as the input of g of x, and then you find your final answer. Your turn. So what is f of g of negative 3 for the functions f and g defined as f of x equal to x minus 5 and g of x equal to x squared? Looks very similar to the previous question, right? You're almost like, Mr. McDougall, why are we answering the exact same question? Well, first off, I want you to take note that the order here is just reversed. Cool? So instead of g of f of x, which we just found, we're actually finding f of g of x, so it's reversed. The first thing we actually plug into would be g of x. All right? So once you get that, then you can easily find your answer. Final answer on this problem is 4. All right. Using composite functions. So now we've got a word problem. You have a coupon good for $5 off the price of any large pizza. You also get a 10% discount on any pizza if you show your student ID. How much more would you pay for a large pizza if the cashier applies the coupon first? Well, basically what we're doing is we're building two equations. Then we are composing them in two different ways. So let's say that if x happens to be the cost of a large pizza, and let's call c of x the cost using the coupon, then that would be the cost is $5 off the price of any large pizza. So that would be the price of the large pizza minus 5. All right. The other one, let's call it d of x, and d of x is going to be the cost using a 10% discount. So this would be the cost of a large pizza multiplied by 0.1, which is I'm sorry, not 0.1. It's actually times 0.9. Let's talk about that real quick, just so we understand. If you're taking off 10%, you're left with 90%. So figuring out exactly what it is that you're looking for, you would multiply the cost of the large pizza by 90% instead of 10%. In this case, we end up with 0.9x. So d of x is equal to 0.9x. All right. Then basically all we need to do here is figure out exactly which of these would save you the most money. So if we were to do c of d of x, that would mean I'm plugging d of x into c of x. So that would be equal to 0.9x minus 5. All I'm doing is taking this and I'm plugging it into the x value here. That's all. The other way would be d of c of x. And if I were to do that, I would end up with plugging c of x into the x here. That would give me 0.9 multiplied by x minus 5. So in this case, I'm literally taking the discount and then subtracting the coupon. And in this case, I am first subtracting the coupon and then taking the discount, which is going to give me 0.9x minus whatever 5 times 0.9 is. What is 5 times 0.9? 10 times 0.9 would be 9, so that would be 4.5, minus 4.5. Okay. All right, so which one's actually going to cost you more? Well, if the pizza costs $1, then it would be 0.9 minus 5 or 0.9 minus 4.5. Which one's going to be the lower number? This one. So you're actually saving a little bit more money if you apply the discount first and then use the coupon. You can skip that last checkpoint, and that'll end our video for today. Thanks, ladies, and check Canvas for your homework assignment.